You may or may not have seen questions like this, okay, in a math class. You go through and list out, well, Harry has 100 pennies, Douglas has $3 bills, Sally has 30 dimes. If Harry wants to exchange his pennies for dollars, Douglas really only likes silver things, and Douglas is the one with dollars, how does Harry have to get his pennies converted into dollar bills? Well, it's kind of a stupid question. Why would anybody ever do that? Harry just beats up Douglas and takes the dollar bills away. Right? It just solves everything, and we don't have to worry about it. Okay, but this is the kind of thing that you would see in a math class, where they would go through, potentially, at least in a math class, where they would go through and create these kind of silly systems that you're like, this is unrealistic, nobody would ever do this. The point of those questions is not because they're supposed to be realistic. The point is to get you familiar with a process for going through and solving, so that when those units move into something that you don't understand, most people understand pennies, dollars, and dimes, right? But if we somehow change those units into something else, how do you solve the question now? And this is where most people freak out and lose their brains because they have no idea what a Snorlaxi is or a Skittlefart. How can I possibly solve this question? Nothing about the question has changed. Okay? It's the process behind solving it that becomes important. And while these examples of Skittlefarts and whatever it is, Snorlaxi, okay, may seem silly to you, these are no more or less silly than the concept of moles. So everybody freaks out at moles because I can't use moles. I can't use atoms. Can you use pennies and dollar bills? Moles and atoms are really just pennies and dollar bills. It's just a different unit system. The issue becomes is that you've spent 20 years, 50 years, between, let's say 20 and 50 years. It may not be fair, because some people may be younger than 20. Let's say between 10 and 50 years working with pennies, dollars, and dimes. Okay? That natural process you have ingrained into your brain so that you don't have to write anything down. You don't have to think about it. Okay? The problem is when we move into science and we change the units into these kind of arbitrary systems, or what appear to be arbitrary, that we don't work with on a day-to-day basis, we can't internalize it. You have to write it down. Okay? That is all I'm asking you to do within this system, or within this unit, is write it down. Okay? Write down what your process is. Okay? And for those who are saying, well, it's if I want to convert feet into inches, I just multiply by 12, or I divide by 12. That is completely not true. Okay? So let's pick that example because that's nice and easy. I have 36 feet, and I want to get into inches. People say, well, I just divide by 12. What is 36 feet divided by 12? 3 feet. Not inches. That's 3 feet. Does the unit of feet go anywhere when I divide by 12? No. Okay? So that doesn't work. Okay? I need a system that allows for me to do that appropriately. And for those of you looking at, well, it's clearly not dividing by 12. Okay? It's two options. It's either multiply or divide. It's a coin toss. It is literally a coin toss. And if you haven't memorized the process to do that exactly right, you will flip a coin and possibly get it wrong. When we do a single conversion, that's one coin toss, not a big deal. Okay? Arguably, that's a pretty big deal, because if you get a 50% in this class, you're probably not going to be happy with your grade. Okay? But what if you have to do two conversions? If you do error propagation with two 50% options, the odds that you get the question drop from being 50% to 25%. So if all you're doing is guessing, should I multiply or divide? Let's just do multiply. The odds that you get the question right, 25%. That is abysmally failing. That is, don't even calculate anything, just blind guess with a multiple choice question. Okay? That is the process I don't want you to do, because that is not successful. So when we go through to do a conversion like this, it's not just divide by 12 or multiply by 12. It's acknowledge what am I trying to do. I want inches in the numerator. How do I know I want inches in the numerator? That's what my answer says. I want inches in the numerator. That's where it belongs. What do I not want in the numerator? Feet. Feet started in the numerator, so it has to cancel. So I want to make sure that feet shows up in the denominator so that those units will cancel. Now that the unit system is there, I can ask the question, what is that conversion factor? What is the relationship between inches and feet? Well, there are 12 inches in 1 foot. Now I have the mathematical system to tell me I need to multiply through. Okay? All we've done is establish the work behind it. Okay? That's all I want you to do now. Okay? That is the whole point of this. Do you guys want to go through and solve the question on your own? The whole Skittle farts and Snorlaxy? Seeing some no's on that, so we'll let that slide. Okay? So, compound units are really just another conversion factor. So what are the units for the speed of your car, your bike, or if you walk to class? Miles per hour, or MPH. Oh, it's MPH. I went 65 MPH on the freeway. No idea why people were honking at me, because you were in the wrong lane. Okay, move over. So what is MPH? Miles per hour. What does that mean mathematically? We have the English. What does that mean? In 1 hour, I have 65 miles. Well, that doesn't look like MPH. How do I get MPH? Divide both sides by 1 hour, and I get 1 equals 65 miles per, there's the division, 1 hour. I have a numerator and denominator. Why do we not establish that and make sure that's extra clear when we talk about MPH? How many people like fractions? Okay. That's all we're doing with conversions, is looking at fractions. Most people tend to freak out as soon as we see fractions. Okay. So we stop writing it in fractions because that hurts people's brains. If we just acknowledge that we get beyond the pain, we can now use that. That is now a conversion factor that allows me to relate hours and miles. Okay, so I can use that to solve a bunch of different questions. Okay, so if I start with a motorcycle traveling 105 kilometers per hour, what is the speed in meters per second? And ignore little white boxes down below because that shouldn't have shown up. Okay, so as we solve all questions, what are we trying to solve for? What does the question ask? Meters per second. There's my English. What does that mean mathematically? That is meters, right? Because we don't like writing out the whole word meters. We would abbreviate as M. What is per? Division symbol, and then symbol for seconds. S. What am I given to start with? I'm given 105 kilometers per 1 hour. Okay. Notice again, we see a slash in our question or in our statement, but how am I writing it? Numerator, denominator. Okay. Why am I writing it numerator, denominator? Because then I can clearly see the numerator and denominator. If I write it as a slash, what is that 105 next to? Any ideas? Kilometers per hour. Okay. Well, that becomes problematic. What is the 105 actually next to? Kilometers. It's not next to hours. It's over 1 hour. That slash organizes it. Well, why the hell do we use the slash then if it confuses us when we try to solve it? That's a good question. Type this into your computer. Type in the fraction into your computer. How easy is that to do? Not so easy. Okay? With new technologies, it's becoming easier. Okay? Remove the new technology and take it back to a typewriter. How easy is it to do a fraction then? It's virtually impossible. That's why we use the slash, because it has an implied meaning back to this, and I can type it easier. That's literally it. Okay? So what you are responsible for doing is taking that kind of, we have to deal with the ancient technology, which is now mathematics, that was modified into fancy technology where we couldn't do that easily. We couldn't draw, and we had to type it into a straight line. And you have to do that constant conversion back and forth into the usable form. Okay? Lots of converting processes. Okay? Most of those should be happening in your head. Okay, so now we look. Is 105 kilometers per hour the same thing as meters per second? No. So what needs to happen? I need to convert it. What do I need to convert? Kilometers. Okay, I could also convert the hours. Okay, I'm going to have to do both at some point. Okay? But if I have to eat breakfast and shower every morning, does that mean I go into the shower and start my toaster so that I can have my toast while I'm in the shower? No, why not? Okay? You'd get soggy toast if you survived the toaster. Okay? We don't do these things at the same time. Break them into different steps. Which one do you want to deal with? I heard kilometers first. Is kilometers in our answer? No. So what has to happen? Where does kilometers in this new conversion need to show up? In the denominator, so that the unit can cancel. Numerator, denominator. What do I want to convert kilometers to? Meters. Do I know the conversion now between meters and kilometers? Okay. Those of you are like, no, I don't know that one. Sorry. Start working on your memorization. That is one that you are required to know. Kilo means 10 to the third. Our power of 10 goes where? Our 10 to the third, our power of 10 goes where in that expression? Okay, in meters. There were a couple people mouthing on top or on bottom. No, they're not going on top or on bottom. It's going with the unit. Okay? The unit, our core unit, is meters. That's where our power of 10 goes. So I will place the power of 10 with the meters. What goes with the kilometers? 1, so that I don't change the meaning of my power of 10. Okay? What happens to the units now? Kilometers cancel, and I would now have, if I ran this calculation, meters per hour. Is that what I want for an answer? No. I could stop, solve, and now move on to the next conversion. The beauty of this dimensional analysis system, because it's all multiplication, I can run it in one sweet, beautiful, long line. And I don't have to break it into individual steps. Okay? Meters is now set, but hours is wrong. Do I want hours in my answer? No. So what needs to happen? I need a new conversion, and I need to cancel out that hours. Well, how did I cancel out the kilometers? I wrote kilometers in denominator. So to cancel out hours, I merely have to write hours in the denominator. Okay. Why does it need to go on top? Okay. It's not that I'm canceling by always putting things in the denominator. I'm placing it such that it cancels, that they're in opposite locations. Okay. So hours in the denominator I want to get rid of. That means hours needs to show up in the numerator. What do I want to convert those hours to? Seconds. Okay. And if you know this, keep your mouth shut. Do you know the conversion between hours and seconds? Some are like, what? It's not 60. Yeah, you're right. Most people don't know that conversion outright. Some people do. You're just smarter than the rest of us. Right? So for those of us that don't know that conversion, what can we convert hours to? We could convert hours to minutes. Why'd you go minutes and not hours to days? Because I don't want to go to days. It's asking for seconds. Well, minutes isn't seconds. Why'd you go to minutes and not days? Okay. We have to realize the relationship between our units. Minutes is closer to seconds. I know the conversion. So what ends up happening is I've now internalized that if I do minutes and seconds here, that one I know. Make sense? Okay. What is the relationship between minutes and seconds? Okay, thank you. 60 seconds in 1 minute. The 60 goes with seconds. Not on the bottom, not on the top, it goes with seconds. Okay? What is the relationship between hours and minutes? Where does the 60 go? With minutes. Right? Don't associate the numbers with numerator denominator, associate them with the unit. Right? So for those of you, because you shook your head, how many seconds are in an hour?
I was thinking of like seconds in a minute.
Oh, okay.
So I was really going to say 60, but that's right.
Yeah. Those of you that can do that math, it's 3,600. Right? Some people can do that. Yeah. The only reason I know that is because I've solved this question a couple times. Right? So now that we've got our unit system set up, what happens? Hours cancels, minutes cancel. What would our answer be if we looked at just the units? Well, does kilometers show up? No, I just showed a slash through it. Does hours show up? No, there's a slash through it. How about meters? Yeah, meters in the numerator. Okay. I canceled it. Minutes? There's a line through it. It canceled it. Seconds. So the units that are left on the left-hand side is meters over seconds. What did I want to solve for?
Meters over seconds.
What did I just find?
Meters over seconds.
Okay. My units have now established what I want to do. Now I have all the work. Now it's just a question of entering it into the calculator. Okay. You've got awesome work. You enter it in the calculator and make a bonehead mistake. You still get a multiple choice answer wrong. Okay. With this awesome work on a show your work question, you get most of the points because you've shown that you know what's going on. You're just dyslexic when it comes to the calculator. That's okay. That happens. But find that out now. Find out that you have problems entering it into the calculator so that we can work on that. Does that make sense? Okay, so what is the answer? Is it the long one? Oh no, something else. Okay. I mean, I got to actually use a calculator? Yes, I can't do that. Give me way too much credit if you think I can do that in my head. And it looks like I didn't cheat because I think the 1.38 is wrong. And it's certainly not 40. That's the page. Everybody got it? 29.167. Oh, that is what you got. Okay. So your calculator spits out something like that. Is that a correct answer? No, why not? But you entered in the calculator right. We even had a second and a third on this. Why is that wrong? Sig figs. Okay. We'd go back through and look at our sig figs in each of these calculations. How many sig figs in minutes to seconds? That's a definition, which means infinite. Hours to minutes. Infinite. Meters to kilometers. Infinite. First one, 3 sig figs, which means my answer needs to get reported to 3 sig figs. 291. The first insignificant digit is 5 or larger, so I will add 1 to the previous location, and my answer becomes 29.2 meters per second. Make sense? Okay. Is that yes, or you're like, that was too much? Okay, let's test you on it then. How far did it get in 120 seconds? Right? Give you an idea, we've got some boxes here that could potentially be filled in. You are given that you want to get in kilometers, your distance, so there's your kilometers. Our given information was 120 seconds. Right? Officially, we had another bit of given information, but we'll worry about that later. Right? Solve that one on your own. I'll give you a couple minutes. Nice and slow. Right? And because we're actually going to go through and fill in what I would expect those boxes to be, or how I would go through and look at it, and how most students go through and look at it. And then we'll look at what's underneath the boxes and see that they'll actually be different. Okay? And we'll address the concerns on perhaps why. So, step one, always, and everybody hates doing this, write at the extreme right-hand side of your page the unit that you want with an equals in front of it. That is step one, always. Like, but I don't know how many steps I'm going to put in there. Then leave a giant white space. That's perfectly all right. Okay? But we want that spacing out there because you need to know where you are going. Okay? If you have absolutely no clue where you're going, you can't get there. Okay? So it needs to get written down. And don't make the assumption, well, I can read the question. You're doing an interpretation in your head every time you then have to do a calculation. That interpretation will very likely create an error in your calculation. Okay, so write it down. I want to get to kilometers. What am I given? Okay. I'm actually given a couple pieces of information, but I decided to write down the 120 seconds first. Okay, and we'll try with the other information in a second too. Okay. Is seconds the same thing as kilometers? No. So what does that mean? I have to do a conversion. So that's where I can do my times, put a line in. Some people refer to it as railroad tracks. I'm fine with that too. Ideally, I need to get rid of seconds. So I need to write that in the denominator. Again, ideally, what am I trying to get to? Kilometers. So that should show up in the numerator. Okay. Is that a conversion factor that I know? No. Is that a conversion factor that is given somewhere in the information? No. Okay. That is perfectly all right to write. Okay. And if you're writing in pen, this now becomes irritating because we don't know that conversion factor. But if you're writing in pencil, it's not that big of a deal because you can be like, well, I'm just going to erase kilometers. I can't do that conversion. Okay. So now the big question comes in, well, what can I convert seconds to? Minutes. Okay. There's a ton of different things I could convert seconds to, but minutes seems to be reasonable. It's a nice big bulk unit, so we could go through and try and run that conversion.
Can we use the answer from our last question?
Theoretically, yes, but I didn't write down that number, so no. It would work. All the calculations will come out the same. Okay. Do I know the conversion between seconds and minutes? Okay, what is that conversion? Where does the 60 go? In front of seconds. Okay, cool. I've done a good job as far as solving the question goes, because what happened to my unit of seconds? It's gone. I didn't want seconds in my answer. I'm now solving my question. What's the issue? In the process of getting rid of seconds, I also brought in minutes. Do I want minutes in my answer? No. So what has to happen? I need to get rid of minutes. Ideally, what would I convert minutes to? Ideally, I want to go into kilometers. Always keep in mind your goal. I want to get into kilometers. Am I given the conversion factor between kilometers and minutes? No. That again means kilometers sucks as a conversion. I need to get rid of it. And now I've got to convert minutes into something else. What do I want to convert minutes into? Hours. Perfectly all right. I can go through and do that. Okay. What is that conversion? Is that one I know? Okay, what is it? 1 hour is 60 minutes. Awesome, I've gotten rid of the unit of minutes. This is good. But in the same time, I've also brought in this pesky unit of hours, which I didn't want in my answer, so what has to happen? I need another conversion factor, where the hours needs to be gotten rid of. Again, what do I ideally want to convert to? Kilometers. Is that a conversion factor that I know? How do I know it? It's given to me in the question. Now I can use that information. Make sense? Right? What goes in front of kilometers? Why 105? I don't accept that. Because it says so is a little bit better, but not by much. What is in front of hours? Kilometers. So I should write down here kilometers? No. So there's the rub behind this. Okay. Why does the 105 go in front of kilometers? The 105 is closest to kilometers in the given information. That's why it goes in front of kilometers. If the 105 was closer to the hours, then I'd put it in front of the hours. Okay? So now the question is, what is in front of the hours? 1. Because if it is anything other than 1, is the 105 true anymore? No. What happens with my units? Well, hours cancel and I'd be left with kilometers. Now when I punched it into the calculator, or if I check all my unit work, the only thing left over is kilometers. Now I'm good to enter it into the calculator, and I'm good to run with this. Hi. What did you guys get for an answer? 3.5. What's that?
702.
Well, that is a really weird calculator. So 3.5-ish, someone was saying, that works for me.
3.50.
Right, well, since people are actually asking 3.50, would 3.50 be a correct? 3.50 be correct? No, why not? 120 is only 2 sig figs. 3.50 is 3 sig figs. Okay? How else could this question be solved? Okay, remember I said we go through and we look at what we're given, okay, or what we want as an answer. I want kilometers as an answer. But now what am I given to start with? Was I only given 120 seconds? What else was I given? I wasn't given meters per second. That was a solve from a previous question. So that's not a given thing. That was an actual solve. What was I given? 105 kilometers per hour. Okay. Do I have to start with the 120 seconds? No. In fact, I would make the argument that it doesn't make sense to start with 120 seconds. It makes more sense to start with 105 kilometers per hour. Why? The answer I want is kilometers. What does 105 give me? Kilometers per hour. That unit makes more sense because it already sets me up with getting to the correct final answer. So I could write 105 kilometers per hour. Okay, what's in front of the hours? 1. Okay, cool. Why did I place the 105 kilometers in the numerator and not in the denominator? Look at your answer. Where's kilometers written? In the numerator. So why do I place 105 kilometers per 1 hour as opposed to the other way? Because I want kilometers in the numerator. That's where it shows up in the answer. So having the answer there can tell me where to place the unit. Okay? So that is useful because that then places that information in there. But it also brought in this pesky hours. Do I want hours? No. No, so that has to be gotten rid of. Okay? Am I given hours anywhere in the question? No. Okay, so what am I going to have to do? Convert hours into something. Okay? Why are you suggesting minutes? Because I did it in the previous one. That doesn't count.
No, it's closest to seconds.
Okay? I look back at the information given, and I'm given something about time. I'm given 120 seconds. Minutes is closer to seconds than is hours. What is the conversion between hours and minutes? 1 hour, 60 minutes. This gets rid of the hour unit. Phenomenal. But again, I've now brought in the minute unit that I don't want. Am I given just minutes? No. So what am I going to have to do to minutes? Convert it into something. So I'm going to convert it into seconds. Okay, what is the conversion? 1 minute is 60 seconds. Okay, awesome, I got rid of minutes, but I don't want and I brought in seconds. Okay, do I want seconds?
Yes.
I don't want seconds in my answer, so I need to do another thing. Okay, I'm going to put seconds in the numerator. Am I given seconds?
Yes.
Yes. What goes in the denominator? The number 1. Why 1? Because I don't want to change the meaning of 120. If it's a number anything other than 1, I'm not looking at 120 anymore. Okay, what unit goes down there? Nothing. Because if any unit goes down there, I'm not looking at 120 seconds anymore. I'm looking at 120 seconds per some other unit. Okay? A lot of students don't like that. Okay? They don't like just leaving that empty. It's not empty. It still holds meaning. If you go all the way back here, you're like, but it's okay to leave it empty in this line. It's not empty up at the top line either. It's over 1. It's still got a denominator in it. Both ways will get the exact same answer. Are both ways identical for thought process? Kind of. Right? That depends on how well you go through and see the relationships between those. Which one do you find easier? Pick that one, solve all your questions that way. Okay? Again, at this stage, what you should be doing is playing around with different methods to make sure you can consistently get the right answer and show all that unit work. Okay? So there's 2 different methods. So let's go ahead and look at the boxes underneath. Whoa, what? The first thing I put in there is 105 kilometers per hour. That did absolutely nothing to my unit canceling. Why would I do that? It's given information. It also places kilometers in the numerator, which I know has to happen at some point. Okay? Again, a lot of people don't like doing that because I've now made things more complicated than what I started with. I now have 3 units that I need to get rid of as opposed to just 1. Okay? So now I have to go through and say, well, how do I get rid of some of those units? Well, kilometers I don't want to get rid of. What do I want to get rid of? Hours and seconds. So I'll come up with a conversion factor that could potentially get rid of hours or seconds. I don't remember which one it is. I got rid of seconds. Okay, cool. So I've simplified my calculation, and I've gotten rid of the units of seconds. But what's the problem? I now have hours and minutes. So what can I do? I can do the hours and minutes. Okay? The order in which we do these conversions is not critical because it is all multiplication and division. Okay? Whichever way clicks for you and you're like, I see that, stick with that. And that's one of the things that makes conversions tricky, is everybody will see it slightly differently. Okay? So if you go to a tutor and ask for help, they may show you a slightly different spin on it because they see something slightly different than you do. Okay? Make sure that when you sit down with a tutor or me, that you at least align and see that solve. Make sense? Okay. So with that, we're going to go ahead and move on. We talked about percents. Should we talk about them again? I don't really like percents, so if someone's shaking their head no, that's all I needed. If you want help with that, you can talk to me after class. Volumes. Right? So we've looked at mass, we've looked at some now distance conversions. What happens with volumes? Volumes bring in an extra tricky aspect because volume was created around solids. Because if I take a cube, I could measure the volume of that cube by taking the length times the width times the height. But those are all distance measurements. Okay? And if I did that calculation, I would get a volume with respect to distance units. So what would the volume of this cube be? And for those of you about to shout liter, stop it. Length times width times height, right? What is the length on this? 10. I disagree. 10 centimeters, thank you. What is the width? For those of you laughing, oh, that's silly. It's not as silly as it sounds. Okay? Include your measurement. Okay, the next one, 10 centimeters. The next one, 10 centimeters. So this would be equal to 10 times 10 times 10, which is 1,000 centimeters cubed. Centimeter begins with, literally, what does centimeter begin with? Easier than that, not centi. C. What does cubed begin with? C. Like, why does that matter? Give me 1,000 cc stat. What are they talking about? Cubic centimeters. Okay. So if you're in a hospital and they're talking about cc's, it's a cubic centimeter. Okay. It's a volume measurement. That's where it's coming from. Okay. So what we established for our volumes was that cc, as it's fun to say, or even cubic centimeters, is too much effort. Okay? And I want to shift that unit into something simpler. Okay? Well, what is simpler than 3 symbols? Well, 2 symbols. That's why I went to cc. What is simpler than 2 symbols? 1. What is the symbol that we invent for our volume? Liters, also known as L. It's a capital L. Right? And so we established that 1 liter is now defined as the volume of a cube that is 10 centimeters on a side. Right? We now have a conversion factor between our volume unit and our volume unit that is a collection of distances. Kind of make sense? How often do we work with liters as a unit in lab? It's too much, so we don't work with it. What do we work with instead? Milliliters. What is the relationship between milliliters and centimeters cubed? So if I take 1,000 centimeters cubed, I want to get it into milliliters. How would I do that? Well, centimeters cubed needs to show up on the bottom. What would need to show up on top? Liters. What is the conversion between those two? 1 liter is 1,000 centimeters cubed. Is that the same thing as milliliters? No. What do I need to do? Convert. Liters on the bottom, milliliters on top. What is the conversion between those two? Milli is 10 to the negative 3. The power of 10 goes with the core unit. What happens? I get 1,000 milliliters. I did all that calculation and you get the exact same answer. Yeah, why do you get the exact same answer? Because 1 centimeter cubed is 1 milliliter. Okay? This is why the metric system is better than the American system. Okay? We have neat little relationships between them that allow us to do these conversions. Okay? So, kind of neat. Our base metric unit, or our core metric unit, is liters, and it is defined as the volume of a cube. Okay? That is 10 centimeters by 10 centimeters by 10 centimeters. Okay? We just did that. So now let's take a look at a new question that shows up with our volumes. This is where it becomes tricky. Okay? An automobile engine displaces a volume of 498 centimeters cubed in each cylinder. What is the displacement of a cylinder in cubic inches? Okay, so let's set this up and then see what you guys can do with it after we get it set up. What do we want for an answer? Inches cubed. And for those of you that were complaining about the whole step one, notice where I'm writing the inches cubed. On the far right with an equal sign, and I'm writing that first. What am I given? I'm given centimeters cubed, 498. Okay. Look at that. I even lined it up relatively close on a straight line. I'm not usually that good at it because I have to zoom in. I can't even see where I'm aiming. You have nice paper because your paper has lines on it. Use the lines. Okay? It's not that horrible. Is centimeters cubed the same thing as inches cubed? So what has to happen? I need to do a conversion. To get rid of centimeters, I need to get inches, right? Do you know that conversion? Sorry, because I wasn't recording. Let's go through and try that again. So your point here, okay, is for those units to cancel, that needs to be centimeters cubed, right?
No, or you could just do it 3 times.
You shush your mouth. That unit needs to cancel. So let's make it centimeters cubed. But if I do that, of course, it then becomes inches cubed, right? And now it works, right? What do you mean it's a trap? What were you suggesting, London? Because you said this, you didn't suggest this. No, you were like, I don't like that. Okay, what were you suggesting?
I was saying that you could times that. So do that exact same thing again, and then basically they'll knock it down to 2, and then
Because that would be in centimeters squared, right?
Right. Centimeters squared, and then do it again, and they'll knock it down to 2, and then multiply.
And that would be centimeters cubed. Okay. Is that going to get a different answer than if I just do cubed and cubed? It shouldn't. The problem is, when we go through and drop that cube in, what are you cubing? You're also cubing the 2.54. Is that what you thought to do? No. Okay? So what ends up happening when you go through to just say, oh, all I got to do is make it cubed, you end up only cubing the unit and not cubing the number. The number is part of that. Okay? So if you're going to do the cube, you have to make sure you cube the number. Okay? So what would that look like? So London's suggestion is, in my opinion, the best way to do it because it very clearly shows each of those steps and you see the unit and the number all the way through. Okay? And I would agree with that method. Most people don't like that because that's the equivalent of, if you remember when we talked about that in class, saying write down 4 times 4 times 4 times, I'm already tired of doing it. Okay? I had 4 times 4 several times. And I don't want to do that. I just wanted to write that as 4, what did I do, 6 times? 4 to the 6th. Okay, so the power of the exponent is useful as long as we make sure it applies to everything that matches it. Which means if we go through and do this, we could have done 1 over 2.54 centimeters, inches, that value cubed. Now the cubed applies in. Right? That cuts down some of those shown work. That still increases the odds of you entering into the calculator wrong. Okay? That's why the top method, as London was suggesting, is the method I would recommend, because it is very difficult for students to not do that division 3 times when it's written out that way. If you make the shorthand, you almost always forget to do the correct division. Does that make sense? Okay. So the answer you come up with, yeah, should be, because I got the work there, might as well do it. Calculator, I believe, spits out 30.3898, right, which of course would be wrong because sig figs. How many sig figs in 1 inch to 2.54 centimeters? That is infinite. It's a definition. That's one of those weird exceptions. Right? That's an infinite sig fig, which means the previous one is infinite, previous one's infinite, and our first one dictates at 3 sig figs. 33, first insignificant, bigger than 5, add 1, and my answer becomes 30.4 inches cubed. Decent? Okay. The length volume conversions almost always trips up students because of that cubing function. You have to watch out for that when you go through and do these. Yes, it will show up on the test. Okay? Make sense? Okay. Any questions about that? Are we good? Good? Oh, yeah.
Why did we apply the cube to 490?
The cubed is only applying, so that cubed there is part of the unit system. Okay. Here, the 2.54 applies to centimeters. 1 inch applies to inches. If I want to run that conversion 3 times to get centimeters cubed, I have to apply it to the number as well. Okay. Here it was given to me as tied to it. Okay. I'm not doing a multiplication or a multiple calculation. It's given to me as that. It's just a tricky statement, but that's the best I got for you. Okay. Other questions on it? Okay. How do we get the volume of irregularly shaped objects? So this is my attempt at irregularly shaped objects. The first one, for those of you in, say, calculus, maybe, if you're in calculus, I think calculus does something like this. We could say, well, those are all triangles. I could measure the volume of each of those triangles, doing some fancy mathematics of whatever it is, 1/2 base times height, right? Is that the volume of a triangle? Well, okay, whatever.
It's like you gotta divide, or you gotta take it by half or whatever.
You do whatever you do to figure out the volume of a triangle. And then we'd say, well, roughly through the middle there, I have an oval, and I could look up the formula for calculating the volume of an oval, and I add all of that up, and I would now have the volume of that object. I don't even want to count how many calculations that is. That's a lot. Okay? But that would work. Right? Approximately, because those aren't perfect triangles, it's not a perfect oval, but it would get pretty close. Okay? How do you measure the volume of that crown? It's now a 3-dimensional object. I can't just take a circle. Okay? I can't take the volume of a cylinder. Well, I could take the volume of a cylinder and then subtract out the volume of the smaller cylinder on the inside, and then subtract out the volume of each of those little jaggy thingies inside it. Okay? That's going to be extra awful. How do I take the volume of... Yeah, what is it? It's a skittle fart. It is kind of a skittle fart. This is my best attempt at trying to get a picture of a gas. It's not that bad, right? It's art. That's all I know. Not with where the dirt's where that gas cloud is coming from. So how do we measure the volume of a gas? Well, the gas changes whatever container it's in. That now becomes a little bit more challenging. Okay? So we want to come up with a way to measure those volumes without having to go through ridiculous amounts of calculations. You've already done Did everybody already do it? Yes? No? This week's lab. So just Tuesday has done it. But Thursday's written a pre-lab where they've provided a procedure about how to measure the volume. So how could we measure the volume? With water displacement. Okay? And my history, which is now kind of slid underneath the stupid volume thing, okay? I think it's Archimedes officially gets credit for it. Was tasked with figuring out was the crown actually made of gold, and to do that he needed to know the volume of it so that he could calculate the density. Okay? And he didn't know how to figure out the volume because it was too hard mathematically to come up with until he sat in a tub and he saw that the water overflowed out of the tub when he sat in it. Well, why would the water overflow out of the tub? Because he was a decent sized guy and someone had filled the tub all the way up, so when he sat down in it, the water overflowed out the edge. His volume displaced the water. Okay? That's where he said, Eureka, I figured it out. And he comes back and he says, I now know the volume of the crown because I know its mass and the volume I can figure out the crown is made of gold. Okay? Or it could be extra fun, the crown was not made of gold, so the king got to kill whoever made him the crown. Because, you know, that's always fun. Okay. So, how do we do that? We take a graduated cylinder where we can measure the volume, okay, nice and easily. We would drop our object into the cylinder. The volume now changes. The difference in that volume is due to the volume of the object. So what is the volume of our jade sample? 10.5 milliliters. I would take 60.5 minus 15. That's it. Okay? So a nice little volume by displacement. Okay, we can do this with a gas as well. The textbook shows this neat little system here. Okay? The idea being is that we do a reaction here, we form a gas, that gas then tries to fill this closed container. Okay? So it's going to increase pressure on that container, causing the liquid to move down away from it or to get away from the liquid. But the only place it can go to get rid of or disappear from the liquid is to climb up this tube and move over to the secondary container. So if this secondary container is graduated, right, meaning it has those markings, I can look at the change in volume there to tell me how much gas was formed. Okay? So that's a pretty neat system. We do have to be a little bit careful with this system though, okay? Because we're looking at a gas, we're looking at heat, and we're looking at volume. And as we'll find out later in the semester, those things are all related. Have you ever taken a balloon and heated it up? Or if you looked out on the horizon out to the east every so often in the mornings, if you're up early enough, okay, you see those weird like balloon shapes floating up in the sky? A hot air balloon, yeah, there you go. Okay, how did it get floating up in the sky? Yeah, you just threw really hard. Okay? It's a hot air balloon. Okay? Those things are deflated. And then what do? They light a fire and they cook the crap out of the balloon, causing the air to expand. Right? And that changes the volume of the balloon with heat. If I add heat here, what am I measuring the volume of? Gas produced or the gas plus the contribution from the heat? I'm getting both. Okay? So this can be a tricky system to use. We have to be a little bit careful with it. Okay? We have to make sure that when we start measuring the volume, that the gas is room temperature. How can I ensure that that's the case? Put this flame really far away from the measuring system. So the tube up here needs to be a decent distance away, so that by the time the gas makes it into my measuring system, it's had time to cool down, and I'm not measuring a temperature effect. I'm measuring only the volume of the gas particles. Okay? So I just wanted to address that because I thought that was important. That's about it. Density. Okay? It is an intrinsic physical property. Okay? The fun thing with density that tends to mess with people is if we go through and look at the pound of lead versus a pound of feathers. Okay? Which weighs more?
It's the same.
It's the same. They both weigh a pound. And someone had given me a fun little link that apparently didn't make it into the lecture, so I'll try and bring it in next week about this. Okay? Turns out it's a massively interesting psychological problem. Okay? There's all sorts of things going on behind this. Okay? But one of the questions that kind of comes out of why people tend to get this question wrong is they don't think about how much it weighs, they think about how much it's going to hurt when it gets swung into your face. Okay? Everybody's probably been hit by a pound of feathers, potentially. Okay? You know, like sleepovers as a kid, what do? Pillow fight. Okay? Probably, hopefully, none of you have been hit in the face with a pound of lead. Okay?
All of us can't even take, a gram of lead.
That's probably true. Okay? So why the sudden change? It's still the same weight. Why do we care? Well, one of the potential explanations behind this is the concept of density that most people don't wrap their heads around very well. Okay? It's the relationship between the mass and the volume. Okay? Both of those weigh a pound, okay? But the pound of feathers takes up a lot more space. So that if I got hit with it, that volume displaces the amount of force so that it doesn't hurt so bad as the pound of lead that comes in screaming as a ball of fist. Okay? And so what we're looking at now is density, the relationship between mass and volume. Well, how would you determine the mass? No. How do you just determine mass? Just weigh it. How would you determine the volume?
Length times width times height.
Length times width times height, if it's a nice square or a nice easy regular shape. What if it's not in a regular shape?
Water displacement.
Water displacement. You can then determine the density of virtually any object, and as long as your measurement of mass and your measurement of volume are both accurate, you should get a reliable measurement for your density. And you can then identify a compound, because all compounds, or most compounds, have slightly different mass to volume ratios. Okay? This is why when you throw a rock in a pool, it sinks, but if I throw a piece of wood in the pool, it floats, even if they have the same mass. Right? It has to do with their density of those individual pieces. Right? The wood can displace that mass over a larger volume so that it floats in the water, whereas the rock sinks. Okay? So what can we do with density? Well, the first thing that comes out of this is now a ratio, a comparison, much like miles per hour. And what did we use miles per hour to do? Convert different units. So what is density? It's another conversion factor. I can now relate mass to volume. Okay. Some other things that we can evaluate with this is depending on the phase that we look at, we may end up changing the units. Okay. So if we look at ice, or H2O, let's start with that. Okay. The density for ice is about 0.917. The density for water is 1. Okay, what were the units on those? Gram, that's the mass, per centimeter cubed. Centimeter cubed, we also said, was a milliliter. Okay. Why did we pick those units? Well, because the number that comes out of that is pretty close to 1. I can manipulate those numbers pretty quickly. What happens when I move to water vapor? For that same volume, what happens to the mass?
Decreases.
It decreases a lot. And awesome person that I am, I covered it up and didn't put it in a way that I could actually see it, so we're just going to make up a number to get the idea. Drops to, say, 0.009 grams. What is the issue with that new number in comparison to the other ones? All right, so sig figs, I'll accept that as a valid argument. Try again.
It's really small, way smaller than the rest.
It's really small. It is so small that I'm now going to have a hard time comprehending what that number means. Okay? Well, if I don't understand what that number means, what I can do is change the units to get that number up to a value that I can deal with on my hands. So volume for gases is typically not in milliliters, it's typically in liters. Because if I scale up to liters, it's the same as multiplying by 1,000, and this number significantly changes. It now gets pretty darn close to 1. So be careful when you look at densities, because depending on the phase, the unit may change. Because we're trying to get the number into a system that we can deal with on our fingers and toes. As silly as that sounds, that's what we're doing. Okay? So, we got a bunch of densities listed out. Do I have gas? I don't, but I don't have the gas for water. Notice the phase or the density for gases though. What's the unit? Grams per liter. Notice the numbers all get a lot. The numbers in virtually all of these are now all pretty reasonably close to each other, right? They're all fingers and toes kind of deals, except the unit changed for the gases. Okay. We changed the unit so that we can get the numbers all close to each other. Okay, why? Because we felt like it.
I'm curious, so say you don't have water as a gas, right? But could you figure it out? Since you have hydrogen and oxygen right there?
No.
Could you take two hydrogen?
Don't try and add the densities because too much changes. Yeah. So what could we ask as far as a question on this? We could go through and do conversions. I would argue the conversions are just like every other conversion, so it's not that big a deal, but we'll pull those up in a second. Okay. I could give you a list of information. Say I've got liquid 2, solid 3, and solid 2. Which of those is the least dense? The one on the top, because it's floating. Okay. Which of those three, solid 2, liquid 2, or solid 3, is the most dense? Solid 3, because it's on the bottom. Okay. So what you could go through and do is, given a whole bunch of densities for these things, here's a new compound. Where does that compound sit in that scale? Okay. If it is a lower density, it's higher than whatever the substance is underneath it. Okay. What if it is the exact same density?
It's going to be right in the middle.
It could be right in the middle. How would it get to the middle? You would have to place it in the middle for that to happen. Okay? So it's just a question of organizing those in a scaling system. For calculating density, I don't know. Do we want to calculate a density? I heard some no's. So what I'll go through and do is I'll record a short video that looks at both of these density calculations, okay, and post that. So if you want to see how to calculate densities through conversion factors, you'll have access to that. I promise it won't be longer than an hour to do those two questions. I'll probably be under 5 minutes because I'll just go through and do it fast. Okay. We are running a little bit behind, just so you know. We'll be moving into the reactions and moving through those pretty quickly in the coming weeks, or the coming week, really.